I've given you two vectors here. If I throw some weights on them and then add them together, what is that called? A linear combination. Okay. So, did you guys watch the Patriots game last night? No? So, my husband was saying, I hope they score 100 points. And my thought was, can you make 100 points? Like, is that a possible score? And so to phrase it in terms of linear algebra, can you use a linear combination of 2, 3, 6, 7, and 8 to make a 100? The answer is yes. But that's what a linear combination is. You have certain, they weren't vectors, right? The points in a football game, or you could think of them as vectors with one number in them. Like, can you put weights on them, being the number of each kind of score to make a 100? All right, the numbers 4 and 5 in part A, what are they known as? Two possible answers here. Scalars or weights? Yeah. Yeah. And then do the calculation, right? So when you multiply a vector by a scalar, you multiply every entry in the vector by that scalar. So we've got 8, 4 plus 15, negative 10. And then when you add vectors, you add entries. You add like corresponding entries. So 8 and 15 is 23. 4 and negative 10 is 6. Yeah, negative 6. All right, so point for your question, point for each question you got right, 1 point for notes, maximum of 4 recorded on your folder. Okay, so today's Friday the 11th. We're going to talk about vector equations today. And I just want to point out that your first quiz is coming up Friday of next week, so a week from today. And it is going to be dual group / individual, right? So you've got two very similar versions of the quiz. They're not exact, right? And they're not the exact same kinds of questions either, right? But they're pretty similar, same concepts, of course. So you're going to spend the first 35 minutes working on the first version with your group, and that will give you a chance to review. I might even answer a question or two if there's still points of confusion. And then the second 35 minutes is individual. You will be allowed to use a graphing calculator. And at some point, I think next week, at some point, I'm going to show you how to use your graphing calculator to do row reduction. So yeah, yep. There is one question where I ask you to like write it all out and tell me what all the steps are, but for every other question, you can use your calculator to do the row reduction. Save some time. Yes.
Is this two things actually? Is it going to be a lengthy quiz?
It's going to take all class. You spend half the class working on part of it in your groups, and then half the class doing an individual part.
And the other question is you really need
her? You won't really, I mean, you can do everything without it for sure, but it was going to take you longer to do the row reduction for some questions.
We use that.
You cannot use anything that accesses the internet. Yes. Yes. Yeah, I'll ask you to actually solve a system and do things. This won't be about like vocabulary. Yeah. Yeah. Yeah, definitely more like the homework. All right, so let's look at today's lesson. Today we're talking about linear combinations of vectors and how linear combinations of vectors relate to systems of linear equations, because that's what we've been working on up until now. A key concept we'll focus on today is the span of a set of vectors. All right, so I've got two vectors here, u and v, 1, 0, 0, and 0, 0, 1. If I want to compute 3u plus 4v, I'm just putting some weights on each of those vectors. And so I get 3, 0, 0 plus 0, 0, 4. So I would have 3, 0, 4. Right? And 3u plus 4v is called a linear combination. Give another example of a linear combination of u and v. U plus 5v, yeah. You just pick any weights you want, you add them together, and that would give me 1, 0, 5. Yes, you can have a weight of 0. It wouldn't be an empty vector, it would be the 0 vector, if your two weights were both zeros, yes.
Could you make quadratics out of this, or any other combination, like u plus b squared?
Nope, that's where the term linear comes from. We're just making linear combinations. Yep. So what is the name for the set of all possible linear combinations of u and v? The span, yeah. All possible linear combinations of a set of vectors is called the span. So the way we write this is we write the span, and then you curly brackets u comma v. All right, so when I type things, I follow the book's convention of bolding the names of vectors. But when I'm writing on the board, it's hard to bold things, so I put the little arrow on top to indicate that it's a vector. Okay. Give an example of another vector in the span of u, v. Yeah, what's w? Give me some numbers. An actual vector. Any vector in the span of u and v. Sure, 0, 0, 0 is always going to be in the span of. So give me one more, just so that I know everybody understands what kind of things are in the span. 501, yeah. Just you can put any weight on these two and then add them together. Any linear combination of the two vectors is in the span. 101 if you just add them together, yeah. Yeah, anything with 0 in the middle. So that description is going to be really helpful for describing the span using set builder notation, right? So we talked about this a little bit on the first day of class. We practiced using set builder notation. So all my vectors that are in the span look like, switch colors here, look like the set of all vectors, right, such that, so what do my vectors look like? They have 0 in the middle, a real number on top and the bottom, but they don't have to be the same, right? So I use A and B, not like A and A. A and B have to be real numbers. Yep, you could use X and Y too, yep, or X and Z, yeah. Yep. How many elements are in the span? Infinite. Yep. Is the span of a set of vectors always infinite? Give me an example where it's not. If the only vector in the set you're spanning is the 0 vector, right? So it's almost always, right? There's the one exception. If I wanted to take the span of just the 0 vector, right? That's a vector that has all 0 entries, right? That only has one element in it because it doesn't matter what weights you put on it, you get the 0 vector. So say that again. No. So a vector that has 0, 0 is a different vector than 0, 0, 0. We call them both the 0 vector, but Oh, no, no, it does not have an infinite number of zeros. It's got any vector where all the entries are 0, we call the 0 vector. Right. Even though we call them the same name. Yeah. Yeah. Typically, you'll be working in some context, like we'll be living in R3 or doing a problem in 3-dimensional space. And so when I say the 0 vector, you'll know I mean the vector that has 3 zeros in it, right? Yes.
For number 2 here.
Yeah.
We can set a matrix to.
Yeah, we're getting there. We're getting there. Is the 0 vector always, sometimes, or never in the span of a given set of vectors? Always, because if you take all of your weights to be 0, you'll always get the 0 vector. So this one's always. The 0 vector is always in the span of any set of vectors. All right, so here are 3 questions that all mean the same thing, and you answer them all the same way, right? Is 4, 12, 4 a linear combination of 2, 1, -3, and 6, 5, -7? That's saying, are there weights that you can put on these two and add them together to get 4, 12, 4? Right? Or I could ask a different question that means the same thing. Is 4, 12, 4 an element of the span of those two vectors? Right? Because span just means all linear combinations. So if 4, 12, 4 is a linear combination of those two, then it's in the span. Or I could say, is 4, 12, 4 contained in the same plane as 2, 1, -3, and 6, 5, -7? It's sort of a geometric interpretation of the same question. And there's something slightly confusing in your book, and they use the term plane to indicate not just a 2-dimensional object, right? I know it's confusing. So in R3, a plane is like a subset that's 2-dimensional. But if you're in R5, they consider vectors that are linear combinations of 2 smaller things to be also a plane, right? So it might not actually be a plane, it's just some subset of the space that we're in. So just keep an eye out for that. It took me a long time to figure out why the heck they were in the same plane. They're not in a 2-dimensional plane. They use the plane in a more generic way. In 3D, they actually do mean a 2-dimensional plane. Yeah, yeah, yeah. Because once you get out of R3, you can't visualize it anymore anyway. So like they call it a plane, but like what the heck is it? I don't know. It's some smaller thing, right? Okay, so that's it for the demo. I think I went through like sort of all the vocabulary and concepts from the reading, and now I'm going to have you work through some problems.